In this lesson we deal with the problem of the range of a matrix. The problem of the range of a matrix from the classical point of view, with the treatment of algebra that is used normally, is complex and unfriendly, since to get the range you have to calculate many determinants that must be non-zero. It can also be done by other methods, as the Gauss elimination. However, in this case, as we had promised, let's use the algorithm, that algorithm that is able to solve all these the problems of linear algebra. In particular, let's obtain the rank of a matrix with the algorithm. For this, what we do is the following. Imagine that we are given a matrix, like what you have there in the transparency, and that we want to calculate the rank. So, what we have to do is to introduce the row or column vectors of that matrix, one by one, into the algorithm, pivoting and following all stages of the algorithm, until the end. What's going to happen, is that at some point, if the range of the matrix is not the maximum possible, we will find that we cannot pivot. What happens when we cannot pivot? When we cannot pivot, the algorithm is so smart, that tell us that that vector, the one that we just entered, is a linear combination of the previous ones, and that is detected, because we're going to pivot, and we did not find any vector v, that is, of those that we have not previously used for pivoting, with a non-zero scalar product. That is a sign of alarm, with which we detect that the vector depends linearly on the previous two, and this algorithm has a property, that it will surprise you a lot, and that is very nice. It not only tells us that this vector is a linear combination of the previous ones, and that the range is to be reduced by 1 unit, but, in addition, the scalar products, after pivoting, that is, those under the columns where there are vectors w, what indicate that we have previously used them to pivot, will give us the components of that vector, which appears in the linear combination, depending on the previous vectors. For example, in the transparency that you have there, in iteration 3, we cannot pivot, because there are two columns that are w, and we cannot use them, because they have been used before, and there are two other columns v, whose scalar products, which are in the last row where the t is, are 0. So, we cannot pivot, and we know that this vector is a linear combination of the previous ones, a1 and a2. However, under these columns of the vectors w, in the third iteration, the scalars products are 1 and 2. What does that mean? Well, the w1, as corresponds to the pivot of the first vector a1, of the vector 1 1 0 1, then it means that that is the component by which you have to multiply this vector, and below the vector w2, you have a scalar product 2, which means that the second vector with which we have pivoted, which was 0 1 1 1, will have component 2. Therefore, in the lower part of the transparency, you have that 1 time the first vector a1, plus 2 times the second vector a2 is equal to the third vector a3. You can check it, just calculating it. Then, this algorithm discovers that vector a3 does not contributes to the rank, because it is a linear combination of the previous vectors. In addition, we discover the combination that we have to use to obtain a3. Analogously, when we enter vector a4, in the fourth iteration, the same thing happens again, that vectors w cannot be used for pivoting, and that the vectors v have scalar products 0. Therefore, we cannot pivot. Then, we also discover that the fourth vector a4, is a linear combination of the previous ones, and that the components are the scalar products, that appear in blue. They are 2 and 2. Then the rank is 2, and as you have in the lower part of the transparency, 2 times the first vector a1, plus 2 times the second vector a2, gives you the fourth vector a4. You can now understand that this method is a very simple method, which it does not cost much to apply it, and especially, if you compare it with the traditional method that is used calculating determinants of minors that are different from 0. Next, let's put another example, which is the case of this matrix what you have there. We are going to do the same. What we do is, we introduce the first row vector A1 of matrix A in the algorithm, which is the 1 0 1 2, the one you have there in iteration 1. We start from the unit matrix. As you know, we calculate the scalar products in the row T, and we pivot. No problem. We enter the second vector, which is the second row of the A matrix. The second row is 1 1 3 4, and we calculate the scalar products and pivot. There's no problem either, but when you enter the third vector, which is 0 1 2 2, in the third iteration, as you can see, we cannot pivot. Not being able to pivot is telling us that vector A3 depends linearly on the previous ones A1 and A2, and gives us the corresponding linear combination, which is defined in what is marked in blue, which are the coefficients -1 and 1, so that in the lower part of the left you have -1 times the first vector A1, plus 1 time the second vector A2 is equal to vector A3, that we just entered. Continuing the process, we enter the fourth row, which is the last vector A4, of the matrix, and the same thing happens to us. We get the scalar products, and we find the same thing, that the W vectors cannot be used, because they have been used before, but the vectors V, have scalar products, listed in the row T, that are 0. Therefore, we cannot pivot. So, we also discover that vector A4 is 0 times the first vector A1, plus the second, that is, we discover, although we could have discovered it before, that row matches exactly, with the second. Therefore, it is obviously a linear combination of it, and is 1 time A2. Since the matrix rank is always the number of times we have been able to pivot, and we were able to pivot twice, the range of this matrix is 2, as in the previous case. An interesting application, from this part, is to get a basis of a linear subspace. A typical problem in linear algebra is that if they give us a linear subspace, by means of a set of generators, a set of vectors such that by combining them linearly we can generate all the vectors in the subspace, then, an interesting question is how can you or if you may or may not reduce the number of generators. You already know that there is the basis concept, which is a minimum set of generators. The subspace dimension is the minimum number of vectors required to generate all the vectors. Therefore, an interesting application of this part, is that we can determine a basis, and it's very simple. Let's get it, vector by vector, and trying to pivot. When a vector is a linear combination of the previous ones, we can detect it, because we cannot pivot, and we eliminate it. We continue the process, eliminating all vectors with which we cannot pivot, and at the end, the remaining vectors constitute a basis. An interesting option is that we can choose the order of the vectors, because the resulting basis, when applying this algorithm, depends on the order in which we sort the vector generators. Then, if we have a preference for some vectors to stay in the basis, instead of another alternative, what we have to do is to locate them adequately first. Then, we have to locate in the first places, and in order of preference, the vectors by which we have preference. If we do so, and we apply the method, what we want will come out. Consequently, this method for calculating the rank of a matrix, is a simple and pleasant method, having the advantage of discovering us what is the linear combination of a vector with respect to the previous ones. In addition, it allows us to find a basis.